I'm Jacob. My topic is automatic railway braking system. First, we need to understand the problems here. Human error. Manual brakings cannot work at all time, especially at high speeds. Next, speed regulation. Maintaining a constant speed is not possible as there might be curves and in rainy conditions it might lead to train going off the track. Next is safety imperative. Single braking failure can lead to huge catastrophe where the train can be involved, two trains can be involved in collision in front as well as the rear. Next, energy efficiency. Optimizing braking might improve the energy efficiency and might remove the unwanted energy waste. Next, identification of subsystems. There are total 6 subsystems in automatic braking system. That is reference speed generator. This reference speed generator have reference speed which will be calculated which can be changed by using track data, signaling and map conditions and other conditions. Next, comparator. It detects here the comparator is used as a detector which it receives the output, which receives the actual speed and compares it with the reference speed generator. Next, PDI controller. The error will be processed. Error will be processed in the PDI controller. Next, actuator, the actual braking system. Next, train dynamics. It has the train's dimensions like weight, all those etc. Next, sensors. There are 2 sensors I used here: accelerometers and wheel tachometers. This is the single stroke block diagram. The reference speed generator, it is a comparator. It receives the actual speed from sensor 4, which is accelerometer. Then compares it with the reference speed generator, where here the comparison occurs. And after comparing, if the speed is high, then the actuator might work and reduce the speed of the train. And this is the train's dynamics. The feedback and feed forward power. Here, the primary feedback is negative feedback. So there are 2 sensors used here, which is accelerometer and wheel tachometer, which continuously measures the actual train speed and feed it to the comparator, which will compare the actual speed and reference speed. Next, the effect of this primary feedback part is it minimizes the speed error in real time, ensuring the train converges to the reference profile. Next, feed forward part, which optimizes the type used is optional enhancement, which is proactive control. Here the trigger is track geometry data approaching downhill gradient. Next, function. It pre-amplifies the signal the controller to increase the braking readiness before gravity acceleration occurs. The limitation is it depends upon the accuracy, up-to-date track gradient map and other conditions. So sensors, as said before, sensors used to this accelerometer and wheel tachometer. The accelerometer will be measuring the train's actual speed, and wheel tachometer is placed in the axle of the mounted in the axle to measure the rotation speed and converts the wheel's RPM directly into the velocity. Here there are 5 assumptions made here, which is train's mass. The mass is calculated as a constant, but there might be some variations due to passengers getting in and getting out of the tunnel. Next, perfect wheel adhesion. Here the wet conditions are not calculated since it might lead to slip or skidding of the railway track. So here 100% adhesion of the train to the railway track is considered. Next, ideal noise filtering, constant active train and zero track zero. Here are the real world implementations. Calvax Indian automatic train production system, which ensures the safety of trains. It avoids pollution of train in front and rear.